today's goal of this lecture. Today I will see some question about rank 1 matrices. This is today's goal of this lecture. In my previous video, I had elaborately discussed what is the rank 1 matrices. In rank 1 matrices, how look like the minimal polynomial, characteristic polynomial, eigen value. Briefly, today I will discuss this as a review. But at first I will hardly recommend you, if you don't see my previous video of rank 1 matrices, at first see this video. Then today's video would be more easy to understand in better way. Okay? And I have given the link in my description box. Please see my description box. First question about rank 1 matrices. Let me show this question which had come Tifr 2025 exam. The question is, consider the following statement. The statement is, first statement, for any linear map which is defined T from R3 to R3 with two-dimensional kernel. Here, dimension of null space is 2. Then, the trace of T is an eigenvalue. If you know the statement of rank 1 matrices, we all of us know the eigenvalue of rank 1 matrices is 0, 0, 0 and trace. See, here given linear transformation T from R3 to R3, for which there exists one mapping always A, which is 3 cross 3 matrices with a real field such that T of x equal to Ax. Here given dimension of kernel is 2, that means null space of the matrix A is 2. This is given condition. That means rank of this matrix A is obviously 1. We all of us know, since the matrix is rank 1 matrix, the eigenvalue of rank 1 matrix when A is n cross n matrix, then the eigenvalue is 0, 0, 0 n minus 1 times, and other eigenvalue is trace of the matrix. Here this trace of A may or may not be equal to 0. This is the rank 1 matrix. Why the eigenvalue of the rank 1 matrix is 0, 0, 0 n minus 1 times and trace of A? At first see, just as a review, in my previous video I had discussed this part elaborately. Since given null space of the matrix is 2, we all of us know null space is actually equal to geometric multiplicity of eigenvalue 0. This is actually equal to null space of the matrix. Since geometric multiplicity means rank of n minus rank of A minus lambda I, here this is the geometric multiplicity GM, here lambda equal to 0, that means n minus rank of A, this is equal to actually geometric multiplicity, and n minus rank of A is nothing but this is actually null space of A. That means null space of the matrix always equal to geometric multiplicity of eigenvalue 0. And we all of us know the relation 1 is less than equal to geometric multiplicity and geometric multiplicity is less than equal to arithmetic multiplicity. Since I have got geometric multiplicity is 2, That means arithmetic multiplicity is greater than equal to 2. Okay? Since geometric multiplicity is the eigenvalue of 0, dimension of eigenvalue 0, and given the null space of A is 2, that means here the eigenvalue always 0, 0 2 times, and another eigenvalue is lambda 3. It may or may not be equal to 0. And we all of us know trace is equal to sum of the eigenvalue. That means lambda 3 equal to trace of the matrix A. I hope my all viewers are. So the eigenvalue of rank 1 matrices is 0, 0 and trace of the matrix. Okay. So option statement 1 is a right statement, and the characteristic polynomial of rank 1 matrices would be such type: x to the power n times x minus trace of A. So notice the second statement: for any linear transformation T from R3 to R3 with a two-dimensional kernel, then x square divides the characteristic polynomial of T. Obviously this statement is also true, because here the characteristic polynomial would be, this is the characteristic polynomial when the matrix is n cross n, but here the matrix is 3 cross 3. So the characteristic polynomial would be x square times x minus trace of A. So for any linear map T from R3 to R3 with two-dimensional kernel, then that imply x square divides the characteristic polynomial. So option A is a right option. 1 and 2 both are true. I hope my all viewers have understood this two statement clearly. These two statements actually very useful statement. Rank 1 matrix. This is very important for any competitive exam, not only TFR. Okay. Next, I will see question about linear transformation, eigenvalue of the matrix characteristic polynomial, and this question had come ISI 2024 exam. The question is TBA M2 cross 2R such that T square equal to 0 but T not equal to 0. Then which of the following statement is not correct? Option 1, the only eigenvalue of T is 0. Option 2, for all V belongs to R2 omitted 0, either V is an eigenvector or the set V TV is a basis of R2. Option 3, T is diagonalizable, and option 4, T is similar to the matrix 0, 0, 1, 0. Here given T square equal to 0 but T not equal to 0. If we all of us know lambda be an eigenvalue of T, then TV equal to lambda V for some non-zero vector V belongs to R2. Then also TV equal to lambda V, then T square V equal to, all of us know, lambda square V. Since T square equal to 0, that imply lambda square v equal to 0. Since v not equal to 0, that imply lambda square equal to 0. And lambda square equal to 0 means lambda equal to 0, 0. Therefore, eigenvalue of the linear transformation T is only 0. So, option 1 is a right option. Option 2, for all v belongs to R2, omitted 0, either v is an eigenvector or VTV, the set VTV is a basis of R2. Is it true? If v is an eigenvector, then obviously this is true. Now, consider v is not eigenvector. And we have to prove VTV is basis. Linearly independent, we have to prove AV plus B TV equal to 0 for some AB belongs to real number, and we have to, for linearly independent, we have to show AB belongs to real number, we have to show A equal to B equal to 0. They are obviously linearly independent because if the set VTV is linearly dependent, that means there exists C belongs to R omitted 0 such that TV equal to CV. That means this is the scalar matrix where C is not equal to 0. That implies C is a non-zero eigen value. That implies non-zero eigenvalue. C is non-zero eigenvalue of T. But this is not true. I have got for this operator T square equal to 0 but not T not equal to 0, always eigenvalue is 0. So the set VTV always be linearly independent. So obviously for all V belongs to R2, either V is an eigenvector or the set is a basis vector of R2. This is right option. Option 3, T is diagonalizable. What is the definition of diagonalizable? If the operator T is diagonalizable, that implies there exists a non-singular matrix P such that P inverse TP equal to diagonal matrix D, where this D is the, here the diagonal matrix means the eigenvalue would be in diagonal, and since here only eigenvalue is 0, so the matrix would be 0 matrix. And that implies T equal to 0, which is also contradiction because here given T is not equal to 0. Therefore, T is diagonalizable. This is be the wrong option. And option 4, T is similar to this matrix. Since here given T square equal to 0, that means minimal polynomial is x square equal to 0. And for this minimal polynomial, the Jordan block is 0, 1, 0, 0. And here in the question, T is similar to this matrix. Here this is the Jordan block and this is also equal to J transpose of J, and transpose of J is this matrix 0, 0, 1, 0. So option 4 is a right option. So in the question I have given which of the following statement is not correct. So this option is actually true option. T is diagonalizable. This is not true. That means these 1, 2, 4 are all right. Only option 3 is a true. for this question. This is wrong for this question. Only option 3 is a right for this question. I will stop here. In my next video, I will discuss some more question about linear algebra. Because linear algebra, this topic is very important for higher study. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.